Good morning. Let's start today's lecture. The first speaker is Professor Alain Lascoux from Institute Schubert. He will talk about Tableaux and Eulerian properties of symmetric groups.
Thank you. I'm very grateful to have been invited to Japan, and especially to come to this international conference. I believe that I'm the only person coming from South Asia, because nobody is wearing a Chinese shirt. So, but I'm also happy because I discovered that there are so many young people who are using divided differences. 30 years ago, we were the only one in France with Schubert, and there was also two independent teams. So the Mazur had stopped making algebraic computations. So two independent teams, IGM and the Mazur. Well, I must add an historical comment is that there was also an independent team, that's to say Newton defined the divided differences in what was before, IGM and the Mazur. And in fact, what Newton had was really the affine Eque algebra, because what he had was the algebra generated by divided differences, and together with the variable xg. And so this is exactly what is called the affine Eque algebra for type A. So it contains the usual Eque algebra generated by the TI, or it contains the, let's say, the nil Eque algebra and so on. So, of course, nowadays we have double affine Eque algebra. You have to add just affine operation to have a double affine Eque algebra, but nevertheless, there are many things which can be seen directly at the level of this algebra of divided differences. So, which are pure algebraic computations. So, it's okay, so let's introduce Newton algebra. Just to confuse people, but it's steady. It's really interesting to try to write everything in terms of divided difference instead of giving a list of axioms. And well, here this is easy to remember. Okay, so I'm interested in what is called the Breuer order on the symmetric group, and which in fact is due to Eresman, who in 1934 gave cellular decomposition of the type variety, and for which, of course, he used the order. So I believe that the journal is not so difficult to find because it's the annals of mathematics. Of course, you can see it was published in French. So here you have properties of the Breuer order and the symmetric group, and as a matter of fact, Eresman doesn't use permutation. It uses the tableaux that I will introduce just on the next slide. So here, the thick arrows is what you can call the permutoid, that is the symmetric group, generated by transposition, simple transposition. Let's say here I act on places, it's easier. And now the Eresman order is when you have the two middle edges. That's to say, you put an edge every time that the permutation differ by multiplication by a transposition, or on the right or on the left, it's the same, but the transposition which is no more a simple transposition. And so that the level increased by 1, decreased by 1. Okay, this is the Eresman order. In fact, to understand this order, you can do something which is you suppress the vertical edges and the edges which cross, and you put an extra point in the middle. So now the structure becomes easier to understand. It's a distributed lattice. And in fact, it's related to the construction of alternating time matrices. So there are many ways to understand the Breuer order. So the Breuer order is really fundamental in many problems in Schubert calculus. In a sense, we can say that Cauchy-linguistic construction at this level is a regularization of the Breuer order. So Breuer order, well, of course, on this picture, everything is very symmetrical, but now if you take intervals in the Breuer order in a big symmetric group, then you see that the structure is really mysterious and there are properties which are not easy to describe, and for which, for example, you need the Cauchy-linguistic. So, one property that I want to study is that, that I studied with Schutz and Berger, is to understand why you have as many permutations of odd lengths as of even lengths. So here we have we count, so we have 1, 2, 2, 1. So it's too symmetrical, but in general, if you take an interval, then apart from the interval which is reduced to a point, then you have as many permutations of odd lengths as of even length. And it's better to formulate it in let's say, in terms of matrices. This is a simpler way to define it. Given a Rampo set, then the matrix giving the comparison is graded by rank, and so the matrix decomposes. I wrote E equal E0 plus E1 plus E2. So here you compare the element, but you filter according to the length. And so you say that the poset is Eulerian if the inverse of this matrix is just by negating the odd components. So you can formulate this in terms of super algebra if you want. So I'm not able to do such things, but it's a very natural property. And so it means that if you look at what it means that the elements of the entries of corresponding to E2, E4, and so on are determined by E1, E3, E5, as to say the odd element determines the even element. And for this, I need tools. So the first tool are Young Tableaux. And for those people who prefer Lascoux-Chatry passes, I decoded for Professor Ram. Please look. You have a tableau, but the tableau can be considered as an increasing chain in the Breuer order, and it depends exactly on the comparison given by Enesman. So you feel, so the tableau is what is written in black, and you fill in the minimal way, in the Breuer order, you complete the columns into a permutation. And you do it in the minimum way compared to the Breuer order, and you have this object, which is now a sequence of permutation, an increasing sequence of permutation, and which is called LS path. But the problem, if you erase the colors, which is what Lascoux-Bach and Chatry do, then you are losing a lot of operators and polynomials. Of course, you could reconstruct that. So here, I'm interested in using operators and tableaux, and so the Lascoux-Bach Chatry path is not a good model for what I want to say. Except that I will recover the two endpoints of this chain, of course, that I will call left and right P. So, and for this, I need an ingredient which was already presented many times. Jeu de taquin. So everybody has played with the jeu de taquin, but careful, here we are using the Cartesian plane, so the coordinates are in the direction. For good reason we shall see, because we are going to, in fact, interpret this computation in the free algebra. And we need really not to have the planar objects, but to have words. Okay, what do you do with the jeu de taquin? You take two columns of the tableau, and by the jeu de taquin, you exchange the two lengths. So the first move, well, here, we pass from 6 to 4 to 6, 3 to 4. Sorry, it's down. So the two last columns, I take 6, 2, and 4, and I obtain 2, 6, 4. Okay? By pushing in the only possible way which preserves the increasing condition in rows and columns. So this is not really a game because the moves are fixed. So constrained by rules which are keep the increasing condition in rows and columns. So if I repeat the operation, commute first column, second column, and commute second column and third column, and go again, then I will get the same tableau. Let's say it's called the skew tableau from the pass, the bottom pass or the up pass. Yeah.
How you chose the first slide?
Sorry?
Repeat how you chose to do the first slide.
So here, what I say is that I take every time a pair of consecutive columns. And so it's either a tableau or it's a skew tableau. And I switch the two lengths by the jeu de taquin. That's to say, I transform a tableau into a skew tableau packed in the other corner, or conversely. This is the operation is on tableaus of two columns. You just exchange the lengths. So, for example, here, because the pointer is not really working, so I have a column of length 3 and a column of length 1, the bottom, and so I transform it into a skew tableau with a column of length 1 and a column of length 3. And so the moves are very easy and they are forced. So the result here is that, in fact, I have an action of the symmetric group of permutation of columns. And I have also another action of permutation of rows, and which doesn't give the same object, but nevertheless the two actions are closely connected. And so the information that I will record is a flag of sets. That's to say, I'm looking at what is on the left. And I discover, this is a property of the jeu de taquin because I move letters, that this is a flag. That's to say, each set is contained into a bigger set of bigger cardinality. So here, my left tableau is made by the columns of lengths 1, 2, and 3, which are, as you see, which are embedded into each other. The same thing with the tableau on the right. So here, given a tableau, with this construction, I've built two tableaus which are really, they correspond to permutations. So we shall see later. So here, not complete permutation cosets because we do not have all the lengths, but it's really a construction which, given a tableau, gives you two permutations. And a very easy construction. You see, tableaus and the jeu de taquin are a way to realize inequalities, which can be formulated, for example, in terms of Gelfand-Zettling patterns. But it's difficult to manage the system of inequalities when you change the model. And here, it's automatic. You need only to remember that you are allowed to write objects which are increasing in rows and columns. This is the only rule to remember. Okay, so here, I've obtained two objects, but I give the different ways of decoding these two objects, of considering these two objects. So Professor Ham, you can choose the way that you prefer. They are all equivalent. So here, I was looking at the right tableau. I have a flag of set, including flag. But of course, it's the same thing to have this tableau, to write it as a tableau. So now this one will be a harassment tableau. when we complete it. And now if I perform, I will explain to you, if I perform the jeu de taquin rose, I see that this red tableau, in fact, is by the jeu de taquin is equivalent to just a trivial tableau, where the letters are the same in every row. So it's equivalent to have this red object or to have the black object. Okay, but the black object has a shape, and which is 0, 1, 0, 3, 0. Don't forget the 0, which means that the row which contains 1 is empty, 0. The row which contains 2 has 1 element. The row which contains 4 has 3 elements, and so on. So it's the same thing to have this object, or to have this vector, or to have the monomial, which is just taking the vector as the exponent of the monomial. So all these are totally equivalent to the object that are obtained by the jeu de taquin, which are the left and right key. It's a way of encoding exactly the same information.
What was the permutation in this case?
Here is not a complete permutation because the shape is not. Here I have a tableau with letter 1 up to 6, and I do not have 6 rows. But it's, you will see that it's I don't need really to have the staircase shape, a full staircase shape. So here it should be a permutation. You can complete this into a permutation, taking the minimum representative. So it's just a coset here in that case. But we shall see this occur naturally with the measure. Okay. And this is what I say here. If you are computing the measure characters, then, as we have seen in some of the lecture, they are obtained by using the pi operator, the isobaric divided difference. Isobaric means that they preserve degree. So here, what do? We start with a dominant weight, that's say a monomial with decreasing exponent, and we apply all possible products of pi, and by definition, these are the measure characters. And if we apply the maximum number of pi, then what we obtain is a show function. But now we are fortunate because we can really work with tableaux instead of working with monomial, and we have the same algebraic computation, except that now it contains much more information. But I was saying that this construction of keys can be used also to solve some other problem. For example, when you multiply two tableaus, when does the resulting tableau has the shape which is the sum of the two shapes of the input tableaus? And the answer is, well, the right key of the first tableau must be less or equal to the left key of the second tableau, and now the comparison is just component-wise. Either two tableaus have the same shape. If not, it's something just a little technicality, but fundamentally, the comparison on keys now is just the box-wise comparison, and this is exactly how Ehresmann defined his order. He had tableaus of staircase shape, and he said permutation, well, he didn't use permutation, but they are comparable if and only if two boxes are in the same position are, well, the number are in, one is smaller than the other. Okay, and so for example, if you take the square of this tableau, then it cannot be of shape 2, 4, 6. Because the right peak was different from, it was a tableau such that the right peak was different from the left key, and only keys can have squares which have a double shape. The left key was a smaller component-wise than the right key. Okay, but here we are not interested in this problem. So, in fact, I'm in a country where crystal graphs are much used, so I pay my tribute to crystal graphs. So, of course, it's a theory which is much more general than the manipulation that I perform on Tableaux, except that, for example, it doesn't contain the jeu de taquin. So here we need crystal graphs, or the equivalent, but we need also things like the jeu de taquin on rows and columns. And so here, this structure is very nice, but it doesn't answer all the questions about the measure character. Okay, so now, let's see, my vision of crystal graph with Schutzenberg. So in fact, let's see, here I wrote what is called, I fix a number, let's say 3, and I'm interested now in the letters 3 and 4. I ignore the other letter. But I do something more, that's to say I pair the 4 and 3 in such a way that now, after pairing, then the string becomes what you see at the bottom, which is 3, 3, 3, it becomes 3, 3, 4, becomes 3, 4, 4, becomes 4, 4, 4. So a string is like that. So what you have up is what remains after the operation of suppression and pairing is just a sequence of 3 and 4, which is weakly increasing. And so there is no difference in having 3, 3, 3, 3, 3, 4, 3, 4, 4, and 4, 4, 4, and having monomials, x3 power 3, x3 power 2, x4, and so on. So here, this is a construction which, from Tableaux, gives you now something which is in the commutative world, which is polynomial in 2 variables. The only requirement is that with polynomial in 2 variables, you always write the first letter before the second, that's to say. You write monomial xi to some power, xi plus 1 to some power. So here, strings are made for that. And now, you have operation at the commutative level, but now with this construction lives at the non-commutative level. The only requirement is that you can replace a sequence of length n by only another sequence of length n. So the operations that you can lift to the space of Tableaux are the operation which preserve degree. And for example, simple transposition preserve degree. So you have an action of the symmetric group on Tableaux, which interpreted in terms of crystal is just the symmetric with respect to the middle. So here you have a middle. I believe okay, you have a middle and you have a symmetry. 3, 3, 3 is exchanged with 4, 4, 4. Okay, and you have the pi operator, of course, which is given, well, which is written. So, okay, so instead of exchanging the 2 elements, you take the sum of the 2 elements between the 2. But there is one thing which has not been mentioned, is that you have the pi operator, but what is very surprising is that you have also other operators which are just the same, minus the identity. So you take the operator minus the identity. And this operator also satisfies the that relation in the commutative, when they are operating in the commutative world. But, so there are another family generating this, what is called the zero equialgebra. And to compare the two and to use the two families at the same time provides identities. So it's important. And so in particular, you can operate so with elements on the string. So I'll write the operation on the tableau. So it's the same. Pi was taking the sum of all elements which are between the tableau and its image and the simple transposition. And here you take the sum of all elements except, this was minus the identity operator, except the head of your string. So here this is the effect on the tableau of the pi hat operator. And so formally, you can write it in algebraic term, of course. Formally, phi I is the operator. First multiply by xi and apply the divided difference. And phi hat is you first apply the divided difference and after multiply by xi plus 1. So it just left-right symmetry. Doesn't work. Ah. Yeah. So now I summarize, I'm sorry, I'm not an expert, so there are traces of glue and scissors. I tried this. And so, okay, so I want to explain the philosophy of this construction before going to the problem. Is that we have the ring of polynomial, which is commutative. It has a basis, linear basis, which are the restricted de Mazur characters that I wrote like that. I will say. And of course, I have the ring of symmetric polynomial, which is contained in the ring of polynomial. So now, if I lift to the free algebra, I still have, thanks to this construction, I have show functions which are the sum of all tableaus of a given shape, treating tableaus as words. And I have also the de Mazur character because we had operators operating on tableaus, so they really regenerate the de Mazur character at the level of the free algebra. But now, there is a problem, we have lost multiplication. So if we take a quotient, which is called the practic algebra, so it's a quotient by the practic relation, that is the Knuth relation, or you can say two words are equivalent if they give the same tableau by Schoenfeld construction, this is the equivalence. Then, now, if I look at this, now the module generated by show function is really a ring. That's to say, this construction embeds the ring of symmetric polynomial into a non-commutative algebra, which is a practic algebra. Which means that for free, you have every statement, algebraic statement on symmetric polynomial as a description, a non-commutative description for free. So I believe that free is a good argument to say that consumption. So you can take Jacobi-Trudy determinant and so on. You can ignore the beautiful work of Gesell-Viennot because it's really. So the pairing of intersecting class is realized by the practic operation. But, so here, my problem is really to work with polynomials, so I will work with the lift of the de Mazur character, which are built with the phi I operator. Okay, so let's repeat now. How do we build de Mazur character? We have to start with a dominant weight, and so the natural tableau which replaces monomial x1 square x2 is a tableau where all the letters are the same in each row. Bottom row 1, 1, 1, second row 2, 2, 2, and so on. And now you use the operator. And what you obtain is that you obtain positive sum of tableau, which is not clear from the algebraic operation. As to say, it's not clear that you will keep positivity. Especially because now, in the free algebra or at the practic algebra level, then the phi I do not satisfy the blend relation. So you are not sure that even that you close this as an hexagon. But this is a fact, which is not difficult to prove. And here I do the operation. So here, the first tableau, now I apply pi 1 hat. That's to say, I'm looking at the letter 1 and 2.
In the practic algebra, the definition of phi I is the sum of the things in the pi space?
Yeah. Not the sum when you apply to the head. That's to say, it's the sum between an element and its symmetrical. And so here, I want to apply pi 1 hat. So here, first pair 2 and 1. And what I'm left with only the letter 1 at the commutative level, x1 is sent to x2, so here tell me that they have to change this 1 into a 2. Now I'm looking at the operator which deals with 2 and 3, so I have 2, 2, and 2, 2 is exchanged into 2, 3 plus 3, 3, and this is what I've written here, and so on. Each time I put the colors, which is which operator I'm going to use next. Okay, and you see that in this way I've generated all tableaus of a given shape. I do not change the shape in this construction. And so the total sum is the show function in 3 letters of shape 2, 1. But if you restrict, then you will obtain the Masur character. So these are the restricted de Masur characters that I write with a hat, and the other characters, the original character of de Masur would be summation over the Breuer interval. So for example, this de Masur character indexed by 102, the full character would be the sum of 4 characters, 102, 120, 210, and 201. So you have to put the pre-order here. I erase the pre-order because I'm interested only in the generating. So here you have a very easy way to generate sets of tableaus, and we need these tableaus. So, okay, so I give the definition. The definition is recursive, and it's not clear that it works because you do not have the breadth relation, but nevertheless it works. So you are starting with dominant monomial. They are the same for the 2 families of the Masur character. So dominant monomial, where the tableau with 1, 1, 1 in the bottom, 2, 2, 2, and so on. And you use either pi or pi hat. And the relation between these 2 constructions is just that the full character is the sum of all the other characters, the restricted character, sum over the Breuer interval. And the converse formula is that you have alternating sum. So the relation between the 2 is very easy. And so now this KV, they are really a basis of the de Masur module. So you have a set of tableaus, but interpreted as a basis of the de Masur module, which are thus generated by algebraic operators on tableaus. But now, okay, so I want to do a little more because I want to see now the relation with the Eulerian property. So I will take now, instead of taking only 1 copy of the free algebra, I take 2 copies to extend the operators. So here what I use, in fact, is not mysterious, it's the Leibniz formula for a divided difference acting on a product. So here you have this cup operator, which by definition, well, I give this definition. So as before, I was taking in a string an element, the symmetrical one here, theta here, cut the 2 ends of the string. So these are really easy to describe the action. But of course, I do not have the right relation, I have to be careful. Okay, so I hope that now you can accept statements. I take a product of two copies of my dominant monomial, but that I write differently, that I interpret differently, either generating the de Masur character or the restricted de Masur character, and I apply any sequence of cup operators. And so now I have to, if I look at the components, what I really get is, on one side I will get the de Masur character. Remember that here on the left side I was only applying the operator pi I, so there is no mystery. But the information is contained on the right side. And I obtain tableaus, and the statement which is easy to prove as a matter of fact, is that the tableaus that you have on the right are all the tableaux which have a left and right given key. So the left key is the index, what you see U, this U. I denoted keys by either vectors or tableaus and so on. So here you have the left key, but you have also the right key. So what I say is that we have an operator, an algebraic operators on Word, which build tableaus which have a left and right key, a fixed left and right key. So here it looks a bit mysterious, we shall see. Okay, so well, maybe it's not necessary to look at I will present another picture, which is this one. So here, this is a case where I will apply two operators, and I show exactly what it is. So I will apply cup 1 and cup 2, and I will obtain all these tableaus. So here, what I see is that the tableaus that I obtain with a simple transposition, I have a tableau, I get another tableau. So tableaus are denoted, so key tableaus are denoted just by the, instead of the, they are just denoted as a vector. So here the simple transposition gives me, of course, 4 tableaus, applying S1, S2, but I have the other tableaus that I write as labeling edges, because these are the tableaux which have left and right given key. So what I get with the operator S1 theta 2 acting on the pairs of Tamanouchi tableau will be, so it's written here, it must be, okay, it's a single tableau. It's a single tableau, 3, 3, 1, 1, 1, 3. So if I just, and so this tableau is exactly as left key 240 and right key 204. But I have also, for example, 2 tableaus given by theta 1, theta 2, and they are 2, 2, 1, 1, 1, 3, and plus 2, 3, 1, 1, 1, 3. So if you perform the jeu de taquin, you will see that these 2 tableaus have keys left and right key, which are 420 and 204. In other words, instead of looking at the algebraic formula, what we have now distributed our tableau as labels on the set of permutation. Here is the permutation of 420. But here now we realize tableaus as edges for the Breuer order. So here, if I look only at the multiplicity, so now I come to the subject, that if I look at multiplicities, then I have wrote the multiplicities. That is the number of tableaux which have a given left and right key. And so what do I have here? I have the identity that 1, 1. If I look at the pass, I have 1, 1. The other pass will be 1, 3. So 1, 1 plus 1, 3. It's equal to 2 times the number of tableaus which have left key 420 and right key 204. So I have the identity, which is the Eulerian identity. So it's equivalent to what I wrote with matrices, that the number of edges, even edges of even length, is given by the number of edges of odd length. This is the identity which is given by the matrix multiplication. But I have tableaus instead of having only multiplicities. So here I can give a more precise statement. So here we are computing in the free algebra. The advantage is that we can choose now projection on the ring of polynomial. So one of the tableaux, the tableau which is on the right, I just take the product of the letter which compose it. So the interpreted I as xi. But the other tableau, I take the inverse variable. So decoding the computation that we made in the free world, then it's really, now if I look at the operation which is induced in the commutative world, it really corresponds to using the operator that I denote by a tilde. So here, which is minus theta I xi plus 1 product si, which is algebraic operators and polynomials. And now the Eulerian property can be rewritten keeping the evaluation of Tableaux. So the identities that I wrote, that 1 plus 3 is equal to 2 times 2, rewrites, add explicit tableaus, and what I add is this type of symmetry, that to say if I take my two tableaux T and T prime, then I have the identity that T14 divided by T plus T14 divided by T prime. So here I have an identity and rational function. So it's the decoding of what I've done at with tableaus. So taking the evaluation, taking the inverse value. So instead of having just numbers of tableaus, then I have an identity on rational function, which is taking the evaluation of tableau or evaluating with inverse variable. So here this looks a little formal. Let's see it on the figures that we have. So here, taking now more generally so that we can. So we had a construction where we had labels, which were tableaus. Now I'm in the commutative world, so I will take monomials and I will write sums. And so the identity that I have is really, I take as a product. But remember, the left was evaluated in the inverse variable. So it really means that sum of T3 divided by T1, that's to say sum of, I take all the elements on the edge and all the elements on the preceding edge. So this sum minus the middle terms is equal to 0. So I put equivalent when you evaluate in the commutative world. So you have an identity on sets of tableaus. So what it is good for, but we shall see. So the statement is now that I have the same type of property as for the Bru order, but now with these sets of tableaus. Except that the E0 is no more the identity matrix. But so this is where I need this this involution, which is passing to the inverse variable. So I have a matrix, which is a matrix now. The evaluation of tableaus are monomials, and I have a matrix of polynomials. I take the inverse matrix, and what I claim is that the inverse matrix is more or less given by taking the inverse value. So here, this is an example which is better. So for the preceding figure, then I've replaced tableaus by their evaluation. And the result of construction is that the inverse matrix is just, as you see, the correspondence is very easy. You have some minus sign, of course, which are easy to and you have taking the inverse variable. So you have a minus sign, of course, and taking the inverse variable. This is what gives the Eulerian property. And if you evaluate all the variables to 1, then you will recover the number of tableaus. So let's see an application. So here, because this is a conference on Schubert calculus, so now I have to decode this in terms of Schubert calculus, and I will speak of the postulation formula. So now, postulation, what does it mean? It's Latin, Italian word. So, well, for me, it will be easier to. So I take a dominant monomial, that's to say, ample line, well, very ample line bundle, the class of very ample line bundle. I take the function, the genetic, I put a z to have a generating function, so I take the inverse, 1 minus z x power lambda, that's to say x1 power lambda 1, x2 power lambda 2. I multiply it by the class, the structure sheaf of Schubert variety, in the case theory, and I apply the de Mazur operator, that's the maximal de Mazur operator, because it's isomorphism. And so this is the operator which computes the dimension of the H0, so it's just a decoding algebraic geometry problem with that, and I specialize xi to 1. And this gives me a rational function which counts really, well, which gives the Hilbert theory, or which exactly counts the postulation, because the dimension of the H0 of, let's say, the dimension of the spaces of selection of Schubert. Okay, and we needed to put a z because we specialize a variable to 1. So and so what is a combinatorial problem? It's equivalent. It's just counting chains of tableaus such that so the left key, I call a chain of tableau when a sequence of tableaus such that the right key of the first one is less or equal to the left key of the other. So this is a decoding of the problem in terms of tableaus. And so in the case of Grassmannian, it's a computation made by Hodge. He was not able to finish the algebraic computation, but later we came to the rescue. He gave a determinantal expression, but he could as well as given just a rational generating theory, and so he obtained the number of postulation number, but which is exactly to count the number of rectangular tableaux having a left and right column given. But if you interpret rectangular tableau as sequence of partitions, then it's really chains of partitions, that's the same partition. And we, in terms of, in more general terms here, in our, for the flag variety and the general Schubert variety, then it consists in taking, you take a de Mazur character, and the de Mazur character indexed by twice the same index, and the de Mazur character indexed by 3 times the same index, and you specialize also variable to 1, and you must get something that you interpret as just giving the dimension of intersection of the postulation. So here I give you, for example, some a list of polynomial for S4. It's a full list if you just eliminate all the permutations which come from the Young's group and up to symmetric, which is inversion of permutation. This is a full list. And many of you have noticed that there is a polynomial which is in red because this is the Eulerian. This is an Eulerian polynomial. And more generally, you will find Eulerian polynomial of any degree in your list of numerators of this generating series. And so here we could say that we have a construction which generalizes the classical Eulerian polynomial. So now what does it, so in terms of tableaux. So here these are the things that we have to obtain and to interpret. So in terms of tableaus. So instead of computing with a pi, you can compute with the pi hat. The effect will be to just to reverse the numerator of your rational function. So you pass from z to 1 over z, so you have reversed. But you have less term when you use pi hat. So here I'm applying, I take the staircase polynomial, and I'm applying pi 3, pi 2, pi 1. And what I get are, in fact, restricted sum of tableaus, because all the tableaus are built with these 6 tableaus and the key tableau. 4 permutations in here, because 8 permutations, sorry, 2 times 2 times 2, that's given by a simple transposition. And I have 6 extra tableaus, which are the labels of the edges. And now what I have wrapping chains in this set of any arbitrary length, which uses this tableau with the condition once more than right must be equal, less or equal to 0. So I have now my generating function now is written purely in terms of tableaus, and concretely I didn't write the numerator. The numerator is 1 minus z power, which is, in that case it would be 4. And if I look at the expansion of the numerator, then it's in terms of tableau, this is what I get in terms of the tableau. In my function, I really keep the tableau, and I get this sum, and you see there is a minus sign, minus c, t3. So when we want a combinatorial interpretation, well, we want only positivity, but we have the Euler relation. So here I decode in terms graphically the algebraic computation. We have this structure with 8 permutations. I prefer to take permutation of 0, 1, and 3. And we have 6 tableaus, which are labels. And now at the minus t3. But fortunately, I have the Euler relation, so that I can eliminate this t3, 2t3, which is equivalent for represent the number of tableaux to t2, t5 plus t2, t6. So now I have a positive sum, and this explains what I get here. I get 5z plus 10z squared plus z cubed, which is a polynomial, the Euler polynomial corresponding to this situation. So, okay, so there's no mystery in all that I've done. I've used only jeu de taquin and pi I operators on Tableaux. That's operators on Tableaux. And but well, nevertheless, here there is still, in fact, there is still work to do, and I didn't do, which is really well. On a simple structure like that, you see really the elimination process is very easy. It's forced. But a young man or young woman should take the problem now, describe exactly the elimination process, which says that which Euler relation you will take to eliminate the negative signs, and so that there is really a combinatorial explanation